Welcome back, folks. This is lecture number 12. Today, we are going to spend our time working problems. There's very little new material today. Again, this is just a review. With that said, let's get started. This particular problem is relatively straightforward. All we need to do is find the current in resistor 5. However, there's a trap, and you need to make very sure you don't fall into it. To make the point, let's let this value be 7.298711152 mega ohms. And we're going to identify this as a trap. And the reason it's a trap is because this resistor, in fact, both R1 and R2 have nothing to do with the problem. The reason for that statement is you have a series circuit here. So the current through R2 is 2 amps, and the current through R1 is 2 amps. And you remember, you're looking for the current out here. Your opening move for this particular problem is to redraw the circuit. 2 amps, 2 ohms, 8 ohms, and 3 ohms. Again, R1 and R2 are meaningless because they are in series with this current source, and no matter what happens, you will still have 2 amps flowing into this portion of the circuit. Okay, we could call this R box. Again, there will be 2 amps flowing into it. Again, we're looking for the current through R5. Looks like this would be a good time to use the current divider. So the resistance of the box is equal to 1 over 2 plus 1 over 8 plus 1 over 3. We'll solve that with the calculator. 2 inverse plus 8 inverse plus 3 inverse equals inverse equals. So our resistance for that box is 1.043 ohms. And then using the current divider, the current on R5 is equal to 1.043 over 3 multiplied by 2. So that value times 2 divided by 3 gives us about 696 milliamps. That's a relatively straightforward problem. The thing is, you need to recognize that R1, R2 were in series with the 2 amp source, which made them effectively invisible to the rest of the circuit because no matter what, there would always be 2 amps of current flowing into this node right here. Here's another problem. As we get started, I wanted to point out a common error, and that goes something like this. People will look at these two resistors and they'll say, oh, they're in parallel, right? Clearly in parallel with each other. Therefore, I have to calculate them together. And that would not be correct because electrically these are not in parallel. Again, physically they may be in parallel, but electrically they are not. And in fact, this is a series circuit, right? This tail end here is a series circuit. And the value of that circuit is 12 plus 4 plus 2. So this resistor here is equal to 18 ohms. That 18 ohm resistor is in parallel with this resistor. So we could draw another box like so. So we would call this R as 9 in parallel with 18, which gives us, what, 6 ohms? Let's try that. So there's your 6 ohms. And now 6 ohms is in series with R1 and R2. So we could draw yet another circle around this. we would call our total 6. Actually, let's do this. We'll call it 2 plus 6 plus 2, which gives us 10 ohms. Therefore, we can call the source current source is equal to a voltage divided by a resistance. So the source current is equal to 2 amps. While we're here, we may as well rework this circuit, but this time let's work it as mesh. So we'll let that be current A, we'll let that be current B. Our first loop equation is negative 20 plus 2 current A plus 9A minus 9B plus 2A. That is equal to 0. Remember, that's a statement about Kirchhoff's voltage law. When you walk in a loop, the sum of the voltages must equal 0. If we simplify this, we get 13A minus 9B is equal to 20. Now we start our second loop. We would say that is 9B minus 9A plus 2B plus 4B plus 12B is equal to 0. That simplifies to 9A plus 27B is equal to 0. You can put these into matrix form. 13, negative 9, 20, negative 9, 27, and 0. Go to our calculator, set up, equation, 1, and then enter the values. 13 equal, negative 9 equal, 20 equal, negative 9, 27, and 0. When we do that, we find that current A is equal to 2 amps, and current B is equal to 667 milliamps. That tells us that there's 2 amps flowing in that direction and 667 milliamps in that direction. You know what, that's kind of sloppy. Let's bring it over here. So here's that resistor, that R3. We know there's 2 amps flowing this way, and there's 667 milliamps flowing that way. So the current in R3 is equal to 2 minus 667 milliamps, which gives us 1.3 amps. Before I forget, this current right here, this was I source, right, which is the same as we got in the previous problem. So I source was 2 amps. So that's this current right here, 2 amps, just like we calculated. Tell you what, while we're here, let's give this problem one more turn, except this time, let's use a little simplification and some Thévenin and Norton transforms to see if we can solve it. So we could start by redrawing the circuit. I think you'll agree that's the same circuit. Here's our 20-volt source, our 20-volt source. We combined R1 and R2 to yield 4 ohms. Here's R3 all by itself as 9 ohms. And the 18 ohms came from here with R4, R6, and R5 together. You may recognize this as a Thévenin circuit. We can convert that to a Norton. So I Norton is V Thévenin over R Thévenin, which in this case gives us 5 amps. And R Norton is equal to R Thévenin, which means this is 4 ohms. We'll keep that 9 ohm resistor, and we'll keep this 18 ohm resistor. To calculate the current through R3, we can use a current divider. The first step is to calculate the resistance of this box. Mode setup. Let's see, back to normal mode. That's 2.4 ohms, and then we can use our current divider. So the current through R3 is equal to 2.4 over 9 by 5. So the current through R3 is 2.4 times 5 equals divided by 9 equals, which gives us 1.3 amps, which is the same solution as our previous calculation. Which calculation is correct? Well, the answer is it doesn't matter. They're all valid as long as you follow the various steps and arrive at the correct solution. Here is another example. Before we start, do you remember what this nomenclature means? That means we took our voltmeter and we connected it to the circuit like so, such that the red was on the positive and the black was on the negative. What we want to do is we want to solve for the voltage on R1. This problem is a question of focus. And what you need to do is you need to focus in on this piece right here. The trap that a lot of folks fall into is they focus on the entire problem, and that gets people in trouble really quick. You need to focus in only on R3. And what you need to consider is that power is equal to IE is equal to I squared R is equal to voltage squared divided by resistance. In this particular problem, we know power and we know resistance. So we cannot calculate that, but we could calculate I squared R or E squared divided by R. And since we're looking for a voltage and something about KVL, we can use this form here. The power is 50 is equal to the voltage across R3, and we'll call that E squared, over this 20 ohms. Solving for voltage, that is the square root of 1,000. So voltage in this case is equal to 31.6 volts. Knowing that, we can use KVL. Starting in that corner, negative 100 plus the voltage on R1 plus 31.6 plus 10 is equal to 0. Solving for voltage on R1, we see that that's 58.4 volts. Another problem. You are looking at a circuit with 3 batteries. These are lead acid batteries, and they are in various states of charge. This one here has a good happy charge on it. This one, not so much. Still, we've taken all 3 batteries and we've put them together on one common grid. The easiest way to solve this problem is to recognize that that's a Thévenin circuit, that's a Thévenin circuit, and that's a Thévenin circuit. If we were to take each of those Thévenins and convert them into Norton, we would find that everything is in parallel with everything. So this first one yields a current of 1,220 amps. And our resistance is here at 10 milliohms. By the way, a Norton current is a Thévenin voltage over a Thévenin resistance, which in this case is 12.2 divided by 0.01. There we go. That's where our 1,220 amps comes from. We do the same for the other pieces. You'll notice that our battery with the good charge gives us lots of current, whereas this one, not so much. You'll also notice that the resistance is considerably lower for the good charge than it is for the poorly charged battery. At this point, the problem is trivial to solve. Because all of these current sources are in parallel, we simply add them together. gives us 3,013 amps. And the resistors are in parallel, so you can also put them together as we do with parallel resistors. So that's 0.01 inverse plus 0.012 inverse plus 0.015 inverse equals inverse equals. That gives us 4 milliohms, which is quite a low resistance. The final step is to convert this back into a Norton circuit. Remember that the Thévenin and Norton resistances are equal, and that a Thévenin voltage is a Norton current by a Norton resistance. In this case, it's 4 milliohms times 3013 gives us a battery voltage of about 12.05. We could talk about the no-load voltage. Okay, when the no-load voltage is equal to the Thévenin voltage. We could also talk about the short circuit current, and that would be equal to I Norton. Let's add a sidebar while we're talking about the batteries here. When you connect your batteries together, you're going to want to use a thick cable or copper strap to connect them together. And then heavy cables to connect to your load. In this case, a DC to AC inverter. We'll let this be the heavy cable for the negative terminal, and this the heavy cable for the positive terminal. We use heavy cables to prevent something called I²R loss. Now remember that power is equal to IE is equal to I²R is equal to E² divided by R. So we talk about I²R loss. It's this one right here. It goes something like this. When you connect your load out here, a certain amount of current will be drawn by the inverter. So you end up with a current flowing in this wire here. If that wire has a large resistance, you will have a large power loss in the cable. Schematically, it looks like this. So here's your voltage for the batteries, and here's the 4 milliohm internal resistance of the batteries, and this is your wire. You wouldn't think it's that important, but as this current approaches 100 amps or 200 amps or more, that wire resistance can have a profound effect on the performance of your system. It can also be downright unsafe if the wire is too small, because the wire can get hot enough to actually melt the insulation. This can lead to some spectacular failures. In the description below, there is a link that shows what can happen when cables go wrong. You can see that the cables will catch fire. You can also have damage to the batteries. For example, if the cables short to each other, that means you've shorted battery to battery, and that can cause the battery to outgas, and that gas can actually catch on fire, depending on the battery chemistry, of course. While we're here, let's talk about a method to determine the current flowing in this system. So this device here is called a shunt. And it looks something like this. This piece is an insulating mounting base. Here are the wires, which are bolted to this material, which is typically brass. And between those squares, we see some very thick wire, which forms a resistance, such that when you have 500 amps of current flowing, there will be a voltage, terminal to terminal, of approximately 50 millivolts. Using Ohm's law, we would say the resistance is equal to 0.05 over 500, which gives you 100 micro ohms, or 0.1 milliohms. So very low value resistor. That very low resistance shunt is placed right here in series with your system. And that provides you a way of measuring current without disturbing the actual circuit. Again, you measure current by the voltage drop across this shunt resistor. It looks something like this. We've got the battery, we've got the Thévenin resistance of that battery, and here's the resistance of your wire, and here's your shunt resistance, and finally your load. So this is our Thévenin, this is our wire, and this is our shunt. As an example, if your current is 100 amps, we would expect the voltage, right? We would expect this voltage here to read 100 times 0.0001, which gives you 100 times 0.0001, which gives you 10 millivolts. One of the reasons I bring this up is to remind you of something. If you have a current meter, if you have an ideal current meter, it has a resistance of 0 ohms. If you wanted to be more specific, the ideal current meter has a shunt resistance of 0 ohms. Because if you were to break the circuit and put your current meter right there, you want to have the lowest value possible for the current flowing through your meter. Of course, the voltmeters are the other way, which means you could take your ideal voltage meter and put it right here, and it would not load the circuit down at all. Let's see, while we're here, have you ever thought what would happen if you took one of these batteries and put it in backwards? Right? What would happen if you got the polarity wrong? That circuit would look something like this. Here we have a 12-volt battery with a 10 milliohm resistance. That's an internal resistance. We'll let the other battery be the same, except this time the polarity is backwards. So this is our circuit. We'll let that be 12 volts as well. The current would equal 24 divided by 20 milliohms, which is 1200 amps. And the power in a single battery would equal I squared R. So that's 1200 squared multiplied by 0.01, which is about 14 kilowatts, which is a tremendous amount of power if you are in an enclosure as small as this. You can expect that battery to smoke and boil, and the hydrogen gas may even ignite. If you haven't done so, check out the description. There's a video link in there that you might find interesting. Moving on, let's talk about capacitors. We'll assume this has 0 initial charge. From your note card, you should have an equation that tells you the voltage on the capacitor as a function of time is the final voltage plus the initial voltage minus the final voltage, e to the negative t over tau, where tau is the product of the resistor and the capacitor. This V final is actually the V Thévenin. I want to get fussy. This R is R Thévenin. Our opening move in this problem is to calculate a Thévenin equivalent circuit. So we remove the load and we look in. We would see R Thévenin as 6 plus 2 in parallel with 4. I believe that's 7.3 ohms. So 2 inverse plus 4 inverse equals plus 6 equals, right? So there's your 7.3. The Thévenin voltage is a simple voltage divider in this case because the voltage here is the same as the voltage here because at no load there is no current draw, which means our voltage is 4 over 2 plus 4 by 20. So our Thévenin voltage is equal to 4 divided by 6 by 20. So 13.3 volts. And now we can use this equation. Vc of t is our final voltage, which is the Thévenin voltage. So that's 13.3 plus our initial, we said it was 0 initial, plus minus final, e to the negative t over tau. Tau is Rc, which is 7.3 ohms by 10 farads. So that's 73.3 seconds. And that goes here. Since this is 0, we can simplify it a little bit. Vc of t is equal to 13.31 minus e to negative t over 73.3. Remember that this is the equation that describes the way the capacitor charges. So as a function of time, and this being the capacitor voltage, we see that the capacitor charges to V Thévenin. And if you want, we can add important things. For example, this is tau at time equal tau, which is equal to 73.3 seconds. We know that we'll be at 63.2% of V Thévenin. So that was 13.3 times 0.632. Okay, so that's something to keep in mind. That's about 8.4 volts. So at 73 seconds, we'll be at about 8.4 volts. Back to this equation, it's important that you know how to use it. For example, if I were to ask you to solve for the voltage on the capacitor at time equal 1 minute, you might guesstimate here and you might say, well, 1 minute is almost 73 seconds, so we're going to guess it's about 7 volts. And let's see if we're right. So Vc of 60 seconds is equal to 13.3, 1 minus e to the negative 60 over 73.3. You can cue that into the calculator as 13.3 times pren 1 minus exponent negative 60 divided by 73.3. Remember that you can't close the parenthesis there. What you'll need to do is walk it over the arrow key and then close the parenthesis. So there we are. The voltage on the capacitor at 60 seconds is equal to 7.4 volts. Another way you'll be asked to use this equation is to solve for t given some voltage. For example, if you're at 10 volts, what is this t? So that looks like this. You would say 10 is equal to 13.3, 1 minus e negative t over 73.3, and solve for t. So 10 divided by 13.3, 0.75 is equal to 1 minus e to the negative t over 73.3. 0.25 is equal to e to the negative t over 73.3. And we take the logarithm of both sides to break this piece out of jail. The natural logarithm of 0.25 gives us negative 1.39 is equal to negative t over 73.3. Therefore, t is equal to about 102 seconds. Now we can move on to some phasor problems. In this case, you're given a time domain representation for the voltage, and you're given a phasor for the current. Your opening move is to convert this into phasor form. So a couple of things. RMS voltage is equal to the volt's peak over root 2. In this case, that's 283 over root 2, which is 200. And because we'll need it later, omega is 2 pi f. So 314 is equal to 2 pi f. F is equal to 50 hertz. It gives us a voltage vector of 200 volts at a phase angle of 30 degrees. And our current vector, we may as well put that into polar form. So that's 4 plus 6j. Oops, not working. Let's see, what did we do here? Setup, you have to be in complex mode. So make sure you're in complex and make sure you're in degrees. Let's try this again. 4 plus j6. There we go. Shift, complex, and polar form, please. So that's 7.2 amps at a phase angle of 56 degrees. We should plot those phasors. Real piece, imaginary piece. So 200 at angle 30 and 7.2 at an angle of 56 degrees. At this point, it's good to ask if this is a capacitive circuit or if it's an inductive circuit. And we can do that with the help of Eli the Iceman. And the fact that these phasors rotate in this direction, we see that the current, the 7.2 amps, is ahead of the voltage. So current leading voltage means that this is a capacitive circuit. Now we can move on to calculate the impedance. This is done using Ohm's law, where the voltage is a current by an impedance. So the impedance is equal to the voltage, in this case 200 at a phase angle of 30 degrees, divided by the current, so 7.2 amps at a phase angle of 56 degrees. Our calculator can easily do that, so 200 at a phase angle of 30 divided by 7.2 at a phase angle of 56. We record that as 25 minus 12J. That is ohms. It's a good habit to keep voltages and currents in polar form. because that is what your meter will read. Okay? So if you were to actually do your calculations and then you were to verify them in the lab, you would want them definitely in polar form. For impedances, it's better to leave those in rectangular form, because those are the values that you would actually see in the lab. For example, you would see that as a resistor of 25 ohms, and you would see that as a capacitor with an impedance of negative J12. For example, if you were to construct a circuit, you would see that resistor of 25 ohms and a capacitor at negative J12. The voltage as measured by the meter would be 200 volts. Remember, that's 50 hertz in this case. And the current would be 7.2 amps. And there's our angle. With regards to this capacitor, remember that this is the impedance. From impedance, we know that the reactance is equal to simply 12 ohms. And from there, we can figure out the value of the capacitor as 1 over 2 pi. This was 50 hertz by capacitance. 12 times 2 times pi times 50 equals inverse equals. So we read that capacitance as 2,700 microfarads, or less commonly referred to as 2.7 millifarads. Just a few more examples and we'll call it a day. This problem isn't so bad, but you gotta watch out. There's a trap. Do you see it? The trap is right here. You'll notice that everything has units of resistance except this L1. What you need to do is convert that into reactance. We need to know the frequency of the circuit. We'll let it be 60 hertz. From there, the reactance of L1 is 2 pi f L, which is 1.88 ohms. The impedance of L1 is therefore J 1.88. So just make a line through this and say J 1.88. And from there, the problem's relatively straightforward. We need to calculate this piece here. We'll call that the impedance of the box. And we need to add that to this piece here. 1 over the impedance of the box is 1 over 10 plus 1 over J 7.5 plus 1 over negative J 25. We run that through our calculator like so. Again, remember to use the parentheses or you're going to get in trouble. So 10 invert plus 7.5 J inverse plus negative 25 J inverse equals inverse equals. So that gives us 5.34 plus J 4.99 ohms. Okay, so that's this piece here. So 5.34 plus J 4.99. At this point, it's useful to redraw the circuit. Here's L1, and we said that was J 1.88. Here's R1, we said that was 1 ohm. And then we have the impedance of the box, which we said was 5.34, J 4.99. From there, it's just a series circuit, so the total impedance is equal to J 1.88 plus 1 plus 5.34 plus J 4.99, giving us 6.3 plus J 6.9. So you add up the J pieces, that's 1.88 plus 4.99. That gave us the 6.9. And then you add up the real pieces, so that's 1 plus 5.34 gives us about 6.3. When all is said and done, our equivalent circuit looks like this, with this being J 6.9 and this being a resistor of 6.3 ohms. We could also argue that it looks like this. We could say that it's a parallel circuit with a resistor and an inductor, where that resistor is 12.7 and this inductance is J 13.9. We can verify that real quick, as 1 over impedance is 1 over 12.7 plus 1 over J 13.9. So that impedance is 12.7 inverse plus 13.9 J inverse equals, and there it is, 6.9 plus J 6.3, which means that these two circuits are absolutely identical. You could talk about a circuit as a series, or you could talk about it as a parallel. Know that it is trivial to switch back and forth between these two forms, but we're going to save that topic for another day, especially when we get to transformers. One final thought. When we meet again, we're going to talk about power. On the DC side of the house, we talked about power as just pi. On the AC side of the house, this becomes something called complex power, is equal to the complex conjugate of the current multiplied by the impedance. And this concept of complex conjugate is actually very straightforward. It basically tells us if you have something like this, all you're going to do is pivot it about the horizontal axis. So if you have a vector described as n plus jm, that becomes a complex conjugate of n minus jm. Or if it was in polar form, so you had some n at, say, I don't know, negative 20, that would become n at 20 degrees. I think you'll really enjoy our next meeting because that's where it starts to get real, if you'll excuse the pun. We're going to talk about real power. We'll talk about apparent power, which has units of volts and amps. And we'll talk about VARs, which is volts, amps, reactive. Remember, our reactive components are the inductors and capacitors. And this VARs is a description of the power that flows back and forth between the generator and these reactive components.